Far beyond Earth, nearly 1,000,000 miles from home, the most expensive scientific instrument humanity had ever built, quietly watched the oldest light in existence. Every beam of ancient infrared light that reached its golden mirror carried a message from a time when the universe itself was still in its infancy. The mission seemed straightforward. Scientists expected the telescope to confirm what decades of theory had already predicted. But before we uncover what the telescope actually found, take a moment to subscribe to the channel and help us reach 1,000 subscribers. If you enjoy well-researched science stories told through real discoveries and evidence, your support truly helps us bring you more videos like this. Instead of confirming expectations hidden among the incoming data, another story slowly began to emerge. It wasn't the kind of discovery anyone could dismiss as a simple malfunction. Nothing had broken. No instrument had failed. There were no calibration errors to blame. The telescope continued working exactly as it had been designed to. Yet, scattered across observations collected by different research teams from different survey fields and over different years, the same unsettling pattern appeared again and again. The universe seemed to be revealing galaxies that should never have existed. According to the standard model of cosmology, the framework upon which generations of physicists had built their understanding of the universe, there simply had not been enough time after the Big Bang for galaxies this large, this bright, and this well-organized to form. The laws of cosmic evolution suggested that the early universe should have been filled only with tiny chaotic collections of newly formed stars. Massive, structured galaxies belonged much later in cosmic history. Yet the telescope kept finding them. Even more unsettling was the fact that these were not uncertain observations. Again and again, researchers checked the data. They measured the light. They analyzed the spectra. They confirmed the enormous distances. Each round of investigation ended with the same conclusion. The galaxies were real. No matter how many alternative explanations scientists proposed, the galaxies refused to disappear. That is where this story truly begins. It is the story of what the James Webb Space Telescope discovered when it looked farther back in time than any instrument before it. It is the story of why some of the world's leading cosmologists have spent years trying to understand these observations, hoping the apparent contradiction would eventually fade away. And it is the story of why, so far, it has not. To understand why these discoveries matter so much, it helps to understand what the James Webb Space Telescope was actually built to accomplish. The answer begins with something surprisingly simple. Light does not travel instantly. Every beam of light moves through space at a fixed speed. Because of that, every object in the universe is seen not as it exists right now, but as it existed when the light first left it. The sun, for example, appears as it was about 8 minutes ago because sunlight requires 8 minutes to reach Earth. A star located 1,000 light-years away is seen exactly as it looked 1,000 years ago, long before much of recorded human history had unfolded. Extend that idea across billions of light-years, and the universe itself becomes a time machine. The farther astronomers look into space, the farther they look into the past. If a telescope is sensitive enough to capture the faintest and most distant light ever emitted, it is no longer simply observing remote galaxies. It is witnessing the universe as it existed only a few 100 million years after the Big Bang, when the very first galaxies were beginning to appear. There was only one problem. The oldest light in the universe no longer looks the way it did when it was first emitted. As space itself expands, every wave of light traveling through it becomes stretched. Over billions of years, the wavelengths grow longer and longer, shifting steadily toward the red end of the spectrum. Astronomers call this effect redshift. For the most distant galaxies, that stretching becomes so extreme that their light disappears completely from visible wavelengths and moves into the infrared. Human eyes cannot detect it. Most earlier telescopes struggled to detect it as well. That missing piece of the universe was exactly what the James Webb Space Telescope had been built to explore. After launching in December 2021 and becoming fully operational during 2022, Webb unfolded its enormous 6.5-meter mirror and began examining the infrared universe with unprecedented sensitivity. Its mission was ambitious from the very beginning. Scientists hoped it would capture the stretched light from the first galaxies that ended the cosmic dark ages and illuminated the universe for the very first time. Unlike its predecessor, the Hubble Space Telescope, which worked primarily in visible and near-infrared wavelengths, Webb was specifically designed to push much farther into the infrared. Its powerful NIRCam and NIR-SPEC instruments could observe light that Hubble simply could not reach. Combined with a mirror offering roughly 6 times Hubble's collecting area, Webb became capable of gathering enough ancient light not only to detect unimaginably distant galaxies, but also to separate that light into detailed spectra. Those spectra would reveal exactly how far away each object truly was, transforming faint, unresolved smudges into confirmed galaxies whose distances could finally be measured with confidence rather than estimated from color alone. For the first time in history, humanity possessed an instrument capable of testing one of cosmology's oldest assumptions by looking directly at the earliest galaxies instead of merely predicting what they should have looked like. For generations, those distant galaxies would have remained nothing more than faint, unresolved smudges, mysterious patches of light that no telescope could properly identify. Webb changed that forever. Its greatest advantage was not simply seeing farther than any telescope before it. It was its ability to take a spectrum of the light arriving from those unimaginably distant objects. Instead of estimating a galaxy's distance from its color alone, astronomers could now separate its light into its individual wavelengths and measure its redshift directly. That single capability changed everything. For the first time, researchers were no longer making educated guesses about where these ancient galaxies belonged in cosmic history. They could confirm their distances with confidence. Without that breakthrough, the mystery that followed would never even have been recognized. The earlier telescopes had not been wrong. They had simply never possessed the tools to ask this particular question. Long before Webb ever unfolded its golden mirror in space, cosmologists already believed they understood how the first galaxies should have formed. Their confidence rested on decades of successful observations, simulations, and mathematical predictions, all brought together inside a remarkably successful framework known as Lambda CDM. Its name combined 2 of modern cosmology's most important ingredients. The first was the cosmological constant, represented by the Greek letter lambda, the mysterious force responsible for the universe's accelerating expansion. The second was cold dark matter, the invisible substance whose gravity quietly shaped almost every large structure in the cosmos. Together, they painted a remarkably consistent picture of the universe's earliest years. According to this model, nothing about the birth of galaxies happened quickly. After the Big Bang, clouds of gas slowly cooled. Guided by enormous halos of invisible dark matter, they gradually collapsed into tiny collections of stars. Those first systems were expected to be faint, irregular, and chaotic, lacking the elegant structure seen in nearby galaxies today. Only after billions of years of collisions, mergers, and steady accumulation were those primitive systems expected to evolve into the large, organized galaxies that now fill the nearby universe, including the Milky Way itself. Time was always the key ingredient, and for decades, every major observation seemed to support that picture. One important piece, however, had never been tested directly. No telescope had ever been capable of observing galaxies from that incredibly early era well enough to compare reality against theory. That was one of the reasons Webb had been built. It was designed not merely to predict what those first galaxies should have looked like, but to observe them directly for the very first time. When the first scientific images arrived only weeks after Webb began releasing data, astronomers expected confirmation. Instead, they found a mystery. The problem became so persistent that many astrophysicists eventually began referring to it, sometimes jokingly, sometimes quite seriously, as the impossible early galaxy problem. During the summer of 2022, researchers examining Webb's earliest deep-field observations identified several candidate galaxies whose light had been emitted only about 500 million years after the Big Bang. That represented less than 4% of the universe's current age. Using their brightness and colors, astronomers estimated how many stars each galaxy contained. The calculations produced numbers that simply refused to cooperate. Several galaxies appeared astonishingly massive. According to the very cosmological model scientists had trusted for decades, there should not have been enough massive dark matter, halos anywhere in the universe at that point in history, capable of hosting galaxies that large. Even if every available atom of ordinary matter inside those halos had somehow been converted directly into stars, an assumption researchers already considered extraordinarily generous, the galaxies still appeared too massive. This was not a result that merely stretched the standard model. It appeared to violate it. Naturally, scientists questioned the measurements before questioning decades of successful theory. Estimating the stellar mass of an object billions of light-years away is extraordinarily difficult. The earliest measurements relied on brightness, observed through several infrared filters, rather than a complete spectrum of the light itself. Under certain conditions, unusually bright emission lines can make a galaxy appear far more massive than it truly is. That possibility offered hope. Over the next several years, astronomers returned to these same objects again and again. This time, they aimed Webb's spectrographs directly at them, separating every wavelength of light in search of a clearer answer. Some of those follow-up observations did reduce the tension. One of the most dramatic early candidates turned out not to be an impossibly massive galaxy after all. Closer examination revealed it to be a faint quasar, a comparatively ordinary galaxy whose central black hole was actively feeding. The brilliant light pouring from matter spiraling into that black hole had overwhelmed the surrounding stars, making the object appear far larger than it really was. For a moment, that discovery brought relief. It demonstrated that at least one of the most alarming observations could be explained without rewriting cosmology. But the relief did not last. As Webb continued observing the early universe, new candidates kept appearing, and this time astronomers possessed the tools to verify them far more carefully than before. Instead of making broad estimates from color alone, they measured each object's spectrum directly. And the deeper they looked, the harder the mystery became to dismiss. The explanation surrounding that first object turned out to be surprisingly ordinary. Its incredible brightness had not come from an impossible number of stars after all. Instead, it was powered by matter spiraling toward a hungry black hole. As the gas plunged inward, it became unimaginably hot, releasing enormous amounts of energy before finally disappearing beyond the event horizon. That brilliant glow had overwhelmed the surrounding galaxy, making the object appear far more massive than it truly was. For the scientific community, it was a welcome result. At last, there was proof that at least one of the most troubling observations could be explained without disturbing the foundations of modern cosmology. The standard model remained intact, but relief was short-lived. As Webb continued surveying the ancient universe, more unusual galaxies kept appearing. This time, however, astronomers approached them with far more powerful tools and much greater caution. Among the most important discoveries were two remarkable galaxies later catalogued as GS-Z 14-0 and MOM-Z14. Unlike the earliest candidates, these were not identified simply from their colors. Researchers carefully analyzed their spectra, reading the unique chemical and physical fingerprints contained within their light. Those measurements confirmed beyond reasonable doubt that both galaxies truly belonged to one of the earliest chapters of cosmic history. Their redshifts exceeded 14. The light-reaching Webb had begun its journey when the universe was only about 300 million years old. Even more remarkable was what that light revealed. Each galaxy contained hundreds of millions of times the Sun's mass in stars. These were not rough estimates or uncertain photometric calculations. They were confirmed measurements based on spectroscopy. Their ultraviolet emission told another equally important story. Both galaxies were still producing new stars at an extraordinary rate, indicating vigorous, ongoing star formation rather than the quiet glow of ancient stellar populations. The implication was impossible to ignore. These were not observational accidents or statistical flukes. They were genuine galaxies, large, structured, and actively creating stars, existing far earlier than the standard picture of cosmic evolution comfortably allowed. Instead of fading away as better observations arrived, the mystery was becoming stronger. Then, in 2026, the story took another unexpected turn. The problem was no longer simply one of mass. It became a question of structure itself. A research team from the University of California, Davis studied one particularly massive early galaxy, expecting to find the turbulent chaos predicted for such a young object. Instead, they discovered something entirely different. The galaxy showed no measurable rotation. According to the conventional picture of galaxy formation, this should have been impossible. Young galaxies were expected to be violent places where enormous clouds of gas collapsed inward while gradually building organized rotation. Their stars should have moved through messy, irregular structures that only slowly settled into the familiar disks observed in nearby galaxies today. A calm, organized system without detectable rotation belonged much later in cosmic history. Yet here it was, appearing astonishingly early. Even more troubling, it was not the only example. Around the same time, a much larger survey conducted by researchers at Cambridge examined more than 250 galaxies from the early universe. Instead of finding a population dominated by chaotic, irregular shapes, the researchers encountered something quite different. A surprisingly large number already displayed smooth, settled, and organized structures. Individually, none of these observations was enough to overturn decades of theory. Any single galaxy might represent an unusual statistical fluctuation. Another could be affected by observational uncertainty. A third might eventually receive a perfectly ordinary explanation. But taken together, the evidence began telling a different story. Independent research teams, analyzing different regions of the sky with different methods, continued uncovering remarkably similar patterns. The growing collection of observations was becoming increasingly difficult to dismiss as coincidence. Then Webb revealed something stranger still. Hidden among the countless distant galaxies was an entirely new population of objects unlike anything astronomers had expected to find. Researchers eventually gave them a deceptively simple name: the little red dots. Almost immediately after Webb's first deep-field images became available, astronomers noticed these tiny, intensely red objects scattered throughout the early universe. There were far more of them than anyone had predicted. At first glance, they seemed easy enough to explain. Perhaps they were simply ordinary galaxies filled with older stars, whose light naturally becomes redder with age. That possibility disappeared almost as quickly as it appeared. Webb possessed enough resolving power to distinguish the overall shape of normal galaxies even at these extraordinary distances. Yet no matter how carefully astronomers examined the little red dots, they refused to reveal any extended structure. They remained astonishingly compact. Each occupied a region less than 1/50th the diameter of our own Milky Way, appearing almost point-like despite the telescope's extraordinary resolving power. Once again, the universe had presented scientists with something they had never expected to see. The mystery deepened the moment astronomers tried to explain where all of that light was coming from. If those tiny objects were powered only by ordinary stars, the numbers became almost impossible to accept. To generate so much light from a region that small would require an unimaginably dense concentration of stars, packed together so tightly that the idea began pushing against the limits of what astrophysicists considered physically plausible. Something else had to be hiding inside them. As researchers gathered more observations, one explanation slowly rose above the others. The little red dots appeared to be harboring black holes. Not ordinary ones, extraordinarily powerful ones. Webb's spectrographs were pointed toward hundreds of these mysterious objects, separating their ancient light into detailed spectra. Again and again, astronomers found the same unmistakable signature. Gas was racing around a central object at speeds greater than 1,000 kilometers per second. As far as current astrophysical theory can explain, motions that extreme occur only around a black hole that is actively feeding. The conclusion was difficult to avoid. Many of the little red dots appeared to be active galactic nuclei, galaxies whose central black holes were consuming surrounding matter so aggressively that the brilliant radiation from the infalling gas completely overwhelmed the combined light of every star inside the galaxy. At first, that explanation seemed promising. Then researchers calculated how massive those black holes would need to be. The calculations reopened the very problem they had hoped to solve. Instead of impossible galaxies, they now faced seemingly impossible black holes. Many appeared to contain central black holes weighing millions of times more than the Sun, despite existing inside galaxies that were, according to every available observation, far too young and far too small to have grown such enormous objects through any of the conventional processes astronomers currently understand. In the nearby universe, astronomers have long observed a remarkably consistent relationship between the total mass of a galaxy and the mass of the black hole at its center. Across thousands of galaxies, that relationship holds surprisingly well. The little red dots refuse to cooperate.